When we began our study of probability, our aim was to show how it could be used in evaluating inductive inferences and inductive arguments. In our previous lesson video, we showed how Bayes' theorem can be used to support the inference of a hypothesis on the basis of observed evidence. In this lesson, we're going to look in some more detail specifically at two inductive argument forms we've discussed previously, with a little more help from Bayes' theorem. Our goals in this lesson are to show how probabilities can be used to express the relation of inductive strength, the thing we were looking for when we first started talking about inductive arguments, and also to show how Bayes' theorem specifically can be used to evaluate inductive arguments that take the form of either enumerative inductions or inferences to the best explanation. What were we looking for with inductive arguments? We wanted a way to show the degree of support that the premises offer for the conclusion, since unlike deductive arguments, the premises don't guarantee the truth of the conclusion. We know that a stronger argument is one where the conclusion is more likely to follow from the premises, and we can use probability as our measure of strength. How do we do that? We want to know how likely it is that the conclusion is true, given that the premises are true. That tells us that we want to determine the strength of an argument from a conditional probability. That probability is the probability that the conclusion is true, given that the premises are true. What does this conditional probability tell us? It says, consider the circumstances that make the premises true. Among those, determine how likely it is that the conclusion is true when you restrict yourself to the circumstances where the premises are true. If that conditional probability is high, the premises offer strong support for the conclusion. If the probability of the premises given the conclusion is low, then the premises offer weak support for the conclusion. Keep this in mind as we look at evaluations of the particular inductive argument forms. We'll start with enumerative induction. Remember that an inference or argument has the form enumerative induction if it goes like this. We reason from the fact that all past instances or all previously observed instances have some feature to either the truth of the claim that the next instance we observe will have that feature, or to the claim that all instances have that feature. So here's an example of reasoning from all past observed instances have had a feature to all instances have that feature. Every electron we have measured has had the same charge, so all electrons have the same charge. Note this example is a little bit simplified because the way that the scientific process of discovery worked is initially we made estimates of the charge that were a little off. But the main idea is right and captured well by this argument form. Repeated observations have shown that the charge of an electron is constant. All electrons have the same charge, about 1.6 times 10 to the negative 19th coulombs. We'll see that this example shows that an enumerative induction is stronger when it is based on more observations that fit the pattern. In this case, as we made more observations of the charge of an electron, the more certain we could be that the charge was constant. We can use Bayes' theorem to calculate the probability of our conclusion given the premises, and we'll start by calculating that conditional probability after just a few observations. So here I've written out the formulation of Bayes' theorem where we're trying to determine the probability of the conclusion given the premise. Filling in for our expanded version of Bayes' theorem, we get what appears on the right side of the equal sign there. Looking at what appears on the right side of the equal sign, we have 4 probability values that we need to calculate or determine the values of in order to calculate the probability of C given P. So we need to know the probability of P given C, the probability of C, the prior probability, the probability of P given not C, and the probability of not C, the prior probability that the conclusion is false. So the prior probability of P given C, that's how likely it is that every electron we measure has the same charge, given our conclusion that all electrons have the same charge. Well, if our conclusion is true, other than maybe making some experimental errors, we're guaranteed to observe the same charge every time. So we can say that the probability of our premises given the conclusion is true is 1. We will always observe the same charge given that our conclusion is true. The probability of C is the prior probability that all electrons have the same charge. Now, when the first measurements were made of the charge of an electron by Robert Millikan in 1908, he already had some hint that electrons were a uniform subatomic particle, that all electrons were basically the same. So let's say that he had an estimation of a little bit more than chance or half that all electrons would have the same charge, and let's call it 2/3. Again, some of these numbers are somewhat arbitrary, but I think they give you a feel for how the calculation will work. And particularly what we care about is the difference between the result after just a few observations and the result after many observations. The probability of P given not C is the probability that we observe the charge of an electron, let's say 5 times, and it always comes out the same, on the assumption that our conclusion is false. If electrons are part of every atom, and there are enormous numbers of atoms in the universe, after only 5 measurements, it's still relatively plausible that at least some electrons have different charges. So not C is the case. So again, it's still pretty likely that we make those 5 observations when the mass of an electron isn't constant. So this number should still be kind of close to 1. The probability that we would see 5 electrons with the same charge, given that not all electrons have the same charge. Finally, the probability of not C should be calculable directly from the probability of C, using our formula for the probability of a negation. That's just 1 minus the probability of C, or 1/3. So plugging in those numbers we assigned, we get the probability that all electrons have the same charge, given that every electron we've measured has the same charge, when we've only measured about 5 electron charges. So plugging in the numbers we just looked at, we get a posterior probability of the conclusion given the premises as about 0.69. Note that what we represent at the bottom is that this isn't actually a huge improvement on our initial estimate of how likely the conclusion was to be true. So our prior probability was 0.67, and after 5 observations-ish, we get up to about 0.69. That limited number of measurements wasn't enough to provide super strong support for the conclusion. However, it's now been over 100 years since those initial experiments, and in that time, scientists have actually run over 100 million measurements that show no variation in the charge of electrons. So again, we're going to try to calculate the probability of the conclusion given the premises. This time, when our premises, every electron we've measured has the same charge, accounts for not just 5 measurements, but over 100 million. In this case, we can essentially ignore the values of the probability of P given C, the probability of C, and the probability of not C. And we'll see why in just a second. Let's focus for a moment, though, on the probability of P given not C. So again, that's the likelihood of our premises being true, given that the conclusion is false. In this example, that would be the chance that we see the same charge 100 million times, given that the conclusion is false and not all electrons have the same charge. That should already seem wildly implausible. So originally, let's look at the numbers for a second. Originally, we said that the chance of getting 5 in a row the same was about 9/10. So that means every new observation, we're saying we have about a 98 out of 100 chance of getting a different charge. That 98 out of 100 number is like thinking that it's very likely that every now and then we'll see an electron with a different charge, even if it's the case that most of them have the same charge. The thing is, though, if you do this 100 million times, you have to multiply all those chances together. That uses the simple conjunction rule. That multiplication gives you the chance of getting a different number on the first experiment times the chance of getting a different number on the second, and so on. 100 million times. There is essentially no chance that we could make 100 million observations of the same charge if the conclusion is false. So this number is essentially 0. If you want to be convinced further, try to calculate just 98 out of 100 to the power of 10,000. So that's 4 fewer zeros. Try using that in your calculator. That number will be very small. Then try to calculate 98 out of 100 to the power of 100,000. Chances are your computer or calculator will give you 0 or an error. So the number 98 out of 100 to the power of 100 million, multiplying 100 million times, is a number so small that your computer likely cannot calculate it. So it's essentially 0. Now we'll see why we only need to plug in the value of the probability of P given not C to see how much support millions of observations offer for our conclusion. Since the probability of P given not C is essentially 0, that whole term that it's a part of in orange there can be said to be 0. What's left is the probability of P given C times the probability of C on both the top and the bottom. Since those are the same, they cancel out and give us a probability of approximately 1. And a probability of 1 means something is certain. So after 100 million observations of the charge of an electron, we can be all but certain that the charge of an electron is always the same. Now, not all enumerative induction will be as certain as measuring the charge of an electron. So let's consider a couple of limitations to enumerative induction. The first is that multiple observations only give us an accurate value of the probability of the premises given the conclusion if we're sampling randomly. So it's possible that we see the same observation 10 times in a row, not because we're getting an accurate representation of uniformity, but because our sample in some way doesn't represent all the actual variation in the world. For example, we might think that if there are both black and white swans, we should be equally likely to see either. But black swans are native to Australia. So Europeans initially reasoned from observation that there were only white swans. But that was because their sample was biased. They didn't realize that the probability of their observations, given that all swans are white was a bit misleading because they were only looking at a limited set of the swans. Another limitation for enumerative induction is that we might overestimate the prior probability of the conclusion if we're not considering all the possible alternative conclusions. So maybe we've seen the same observation 10 times in a row, but that's not because the observation supports the conclusion we're thinking of, but instead because it supports some alternative, maybe similar conclusion. So for example, we might observe that 10 swans in a row are white, but that might be not because 100% of swans are white, but actually because 95% of swans are white. And if we don't consider that alternative conclusion, that 95% of swans are white, we might overestimate the support our observations offer for the conclusion we're considering. So we might overestimate the support 10 observations offers for the conclusion that all swans are white, because there is this alternative conclusion that is also pretty well supported by that limited number of observations. We're now going to turn our attention from enumerative induction to another form of inductive inference. That's inference to the best explanation. Remember that in inference to the best explanation, we reason from an observation or some set of observations, and then we conclude or infer the cause that best explains that evidence. So the explanation is not something we directly observe. Instead, what we observe is the evidence that needs explaining, and what we infer is our conclusion. We infer the truth of the explanation for what we have directly observed. We gave some criteria for what made a better explanation when we introduced this pattern of reasoning in Lesson 7. What we're going to look at now is how the evidential interpretation of Bayes' theorem can be used to more precisely characterize what makes some explanations better than others. Remember that the point of the evidential interpretation of Bayes' theorem is to calculate the probability of H given E. The probability that your hypothesis is true given the evidence that you have. Our hypothesis, the explanation for our evidence, that's our conclusion, and the evidence serves as our premises. We can say that one explanation, H1, is a better explanation than another one, H2, if the probability of H1 given our evidence is greater than the probability of H2 given our evidence. This fits with what we said about the relation between inductive strength and conditional probability at the beginning of the lesson. Higher conditional probabilities mean stronger inductive arguments. There are two main ways we're going to consider about what it takes to make a better explanation. First, we want an explanation that explains the evidence better than the other hypotheses, and we want an explanation that is more likely than other hypotheses. We're going to look at what each of those correspond to in terms of Bayes' theorem and how they affect the conditional probability of H given E. If hypothesis 1 explains the evidence better than hypothesis 2, then H1 is a better explanation. The probability of E given H is our measure of how well the hypothesis accounts for the evidence. Since the probability of E given H appears in the denominator, the higher its value is, the higher the probability of H given E. And so the more likely it is that our hypothesis best explains the evidence. Let's consider what this means in terms of an example. So previously in Lesson 7, we talked about an example where you come into the kitchen in the morning and you find a plate and a cup left on the table with breadcrumbs and butter on the plate and then a few other items around there. You want to know what explains the stuff you find on the table. So let's use that example to make sense of this condition on a good explanation. Finding a single plate with crumbs and some things that go on toast and no housemate to be seen, that's all very likely if your messy housemate eats a middle-of-the-night toast snack. If your housemate, though, is normally neat, that makes it less likely that you would see that evidence after a middle-of-the-night snack. So the probability of E given H is higher in the first case than in the second. So in the first case, the hypothesis is better supported by the evidence. We also said that if hypothesis 1 is more likely than hypothesis 2, then hypothesis 1 is a better explanation. So a hypothesis is more likely the higher the probability of H is, and the probability of H is our measure of how well the hypothesis fits with other things we know. As with the probability of E given H, since the probability of H appears in the denominator, the higher its value is, the higher the probability of H given E, so the more likely it is that our hypothesis best explains the evidence. Let's consider again what this one means in the context of our midnight snack example. If you know that your housemate commonly complains about waking up hungry in the middle of the night and is a bit messy, the hypothesis that they had a midnight snack fits well with what you already know about their behavior. So it's pretty likely that it's true. The hypothesis that your housemate tried to make you believe they had a midnight snack by setting things up, that doesn't really fit well with what we know about how people normally behave. So the probability of that hypothesis is much lower. So since the prior probability of the first of these hypotheses is higher than the prior probability of the second, the first one offers better support for the conclusion. Again, when the probability of H is higher, the probability of H given E, what we're trying to calculate, is higher. So the probability of the first hypothesis given the evidence will be higher than the probability of the second hypothesis given the evidence. And that makes the first hypothesis a better explanation. So here are the key takeaways of this lesson. First, the strength of an inductive argument can be represented with a conditional probability, the chance that the conclusion is true given that the premises are true, which we can write as the probability of C given P. The second thing is that with Bayes' theorem, we can show that an enumerative inductive argument gets stronger with more observations. And that's because the chance that multiple observations that fit that pattern go with the conclusion being false, that is, the probability of P given not C, gets increasingly close to 0, so the probability of C given P gets closer and closer to 1. And with Bayes' theorem, we can show that with inference to the best explanation, a better explanation is one where the hypothesis fits what we know, the probability of H is higher, and when the evidence is better accounted for by our explanation, when the probability of E given H is higher. And now you should have a sense of not only how to calculate probabilities, but also of how they are important to evaluating inductive arguments and inferences.